Welcome to this tutorial of the Kratos application. This is the second tutorial of the series, and in this one we are going to see how to set up a parametric full order model simulation using the structural mechanics application. In order to follow this tutorial, you will need to have installed GID, in particular the Kratos problem type, and from Kratos Multiphysics we will need two applications, the structural mechanics and the constitutive laws apps. So this is the geometry that we are going to be studying in this tutorial. So it is a simple beam. It is clamped, so one of the sides is restricted in the x and y directions, and we have three pressures, P1, P2 and P3. The magnitude of these pressures will constitute our parameters vector mu. So let us go to GID and model this. So we open the Kratos problem type on data, problem type, and choose Kratos. Then we are going to select structural and 2D, not 2D axisymmetric, just plain 2D. In here we are going to draw the rectangle, and in particular these are the coordinates that we are going to be requiring. So let me just come here to create line and input each one of these 0, 0, 1, 0, 1, 10, 0, 10, 0, 9, 0, 5, 0, 4, and 0, 0. In this one it asks me whether I want to have 2 points or join. I select join, and that's it. That's the geometry that we need. I will create using these lines. I will create a surface using this create NURBS surface. So I choose that and select all of them, all of the line segments, and that's it. So this will be the geometry. We have created these line segments on top and 2 on the side in order to be able to apply the pressure loads. First thing is we are going to assign to the surface, we're going to assign the material properties. We could go for linear elastic, but just let us go for hyperelastic Neo-Hookean, and that's the only thing that we're going to be changing from the material. Let us directly select that. Okay, that's it. Okay, so we have assigned this material property to the surface. Let us assign the bottom constraint displacement, so it is boundary conditions, displacements, and we choose lines and select the bottom line. Finally, let us apply the pressures on lines. So we'll, just for the sake of entering something, let us put 10 on the top. Okay, let us double click again pressure on lines and select 10 over here, and finally again 10 on here. That's it. So let us save these and let us call it, for example, beam. We create the mesh on this geometry. 0.5 will be 2 chords. Let us just put 0.2. And finally, we go to Kratos and write calculation files now run. We will see on here in this terminal that it says MDPA and JSON written OK. That's it. So if we open the folder where we saved it, we will see that in reality there's a lot of these files .cnd.go, which are only used by GID. The ones that we are going to be needing is MDPA, the main Kratos.py, and the 2 JSONs. Those are the only ones we actually need, but if you want, we can from here directly run the Python file using Python 3 main Kratos.py, and we can just see that the simulation is actually working. So as you can see, it does indeed solve the simulation, but let us just copy our two JSONs, the Python and the MDPA. We're going to copy it in a new folder called RAM, and this is all we need, so we can test that. From here we can also do Python 3 main Kratos.py. It again solves the problem, and here in the GID output we can here, let's open GID. Just as we did with all the other files, only with these 4 files we can also see the simulation. So these are the files that we are going to be needing in order to set up the Kratos simulation within the ROM application. So from in the next tutorial we are going to be modifying in particular the main Kratos.py in order to set up a parametric reduced order model.